Thanks, everyone. All right, so this talk is called How Nakamoto Works, and it is best viewed in a 256-color terminal. I use Xterm, so one recommendation there. 4 topics we'll be covering today are in the new behaviors of the Nakamoto system. So as you might have heard, the Nakamoto has fast blocks, much faster than what it is today. We're talking on the order of 5 seconds for a confirmation, for a transaction confirmation. There's no more forks in the Nakamoto system either. Miners must confirm the stack's chain tip. Forks can only happen if Bitcoin itself forks, and that leads into the third new behavior we have, which is Bitcoin finality. So Stacks right now has an independent security budget of Bitcoin, but with Nakamoto, it will be just as hard to attack the Stacks blockchain, but through a reorg, as it is to attack the Bitcoin blockchain. The final new behavior we have is we are changing a few things about the sortition algorithm to reduce the impact of Bitcoin MEV. That is to say, miner extractable value. That's important to get systems like SBTC to work, as we'll talk about towards the end. This one's probably the spiciest of the 4 things here, so we'll save that one for the end. So how do we achieve all of the above? So the entities in this, so right now we have this notion of a tenure in the Stacks blockchain. When a new Bitcoin block arrives, it contains some block commit transactions that in turn contain the hashes of new Stacks blocks. Stacks nodes everywhere process that Bitcoin block. They independently choose the winning Stacks miner through a process called cryptographic sortition. That miner's tenure begins when that Bitcoin block is processed. Everyone knows the hash of the block they're going to announce. They announce their block to the peer network, and they can proceed to append microblocks on top of that block through the duration of their tenure until the next Bitcoin block arrives. That's changing in Nakamoto. Bitcoin blocks will not derive tenures directly. Instead, stackers decide when tenures happen. And that's important because what this means is stackers are responsible for block replication. If a miner wants to have a block appended to the Stacks blockchain, they have to send it to stackers, and stackers must sign it. They produce an aggregate signature that makes the block valid, and they in turn replicate that block to the rest of the network. Now, what that means is that when a new miner comes online through a new cryptographic sortition, stackers can require that miner to append to the last block the stackers know about. That eliminates forks. And because the blocks are widely replicated, you don't have to worry about blocks arriving late. You don't have to worry about miners not knowing what to build atop. This is guaranteed by stackers being incentivized to make this happen. Stackers must produce a signature that represents 70% of the stacked stacks. And if they don't do this, they don't get their POX payouts because no one's going to mine. And their stacks won't ever unlock because no one can process blocks to do the unlock. So stackers are incentivized to keep the system going. Miners are incentivized as they are before. Only miners get Coinbases. Only miners get block rewards. So with these new responsibilities, the chain looks something like this now. So if you look at the lower left here, we have a Bitcoin block with a Stacks transaction. That purple transaction is the winning Stacks block commit. The arrival of that Bitcoin block doesn't give the miner permission to start making blocks yet. What it does is it tells stackers, hey, we need to change tenure here. Once the stackers can agree that a new tenure has to happen, they can tell the purple miner, you must confirm the last block the green miner produced. This is encoded in a new type of Stacks transaction called a tenure change transaction that is collectively signed by stackers and which miners must include in the first block they produce. Now, once that happens, miners can continue to produce many blocks during their tenure, once every 5 seconds or so. And in the event that it takes more than 10 minutes for a new Bitcoin block to arrive, stackers can grant that miner an extension on their tenure. So they can keep making blocks every 5 seconds, even though the combined compute budget for those stream of blocks might exceed what is normally allotted to them per 10-minute intervals. The system proceeds in this manner until the next Bitcoin block arrives and the blue miner comes online through another tenure change. Just drilling into this a little bit more, Stacks miners begin with step 1 by submitting a block commit transaction. Once the block commit transaction confirms in a Bitcoin block, stackers observe it, and they produce a tenure change with that 70% signing power. Miners obtain that tenure change to produce their first block, and then miners proceed to execute something kind of like a 2-phase commit. Miners make the block, they send the block to the stackers acknowledge the block, they replicate it. Once the miner sees it's been replicated, it produces its next block, and so on and so forth until the next Bitcoin block arrives. So this is great. We have many blocks per Bitcoin block now instead of just one. And the rate at which the rate at which stacks blocks are produced is now governed by stackers' ability to sign them. And that's mediated through these new 10-year change transactions and 10-year extend transactions. Now, that gets us no forks, and the Bitcoin finality component comes from the fact that miners in that block commit transaction no longer need to put the hash of the block they're going to announce, but they instead put the hash of the start of the last 10 years block. What that does is it basically staples the 10-year history of the Stacks blockchain to the Bitcoin chain. So even if all of the stackers get compromised and start trying to do things like sign conflicting histories, they can't undo any tenure from n-2 10 years ago, from 10 years back. They'd have to attack the Bitcoin chain first. What that means is that in the meantime, your transactions are secured by that 70% stacks for the tenure in which it is mined in the following tenure. But once those two things pass, which is the same as waiting for two confirmations, the history of the Stacks blockchain, and thus your transaction, is as permanent as Bitcoin is. So there's three enabling technologies in the Stacks blockchain that make all this happen, and they're each produced by different entities in the ecosystem. The first of which is called weighted Schnorr threshold signatures, or WSTS, and this comes out of trust machines. This is a novel cryptographic protocol that is based on well-understood cryptographic protocols, Schnorr signatures, that allows stackers to produce signatures weighted by the number of reward slots that they have. The signing process doesn't happen in the node, but it happens through a separate daemon that runs alongside the node that carries out the signatures on their behalf. The second enabling technology comes from the Stacks Foundation, and that's called the StackerDB. It's an overlay on top of the Stacks peer-to-peer network that allows Stacks nodes to opt into hosting and replicating data on behalf of a smart contract. It's a generic system, but it was built for this specific purpose here. The POX4 smart contract, the upcoming iteration of the POX mechanism, will encode a StackerDB. Nodes can subscribe to this in order to host copies of the signer state. So signers carry out distributed signing rounds. They coordinate with one another through this StackerDB instance linked to the POX4 contract. The third enabling technology is Clarity WASM, coming out of principally from Hero Systems. We preserve all the same properties of Clarity. What you see is what you get. The source code's on the blockchain. But instead of using a bespoke abstract syntax tree intermediate representation, which is then interpreted to execute the transaction, we're using the WASM as the intermediate representation. And what that leads to is about 100x performance improvement. Clarity WASM increases the Stacks chain's bandwidth, which combined with the low latency of Nakamoto leads to a chain that can do a hell of a lot more than it currently does now. So drilling into each of these, weighted Schnorr threshold signatures comes principally from Joey Yandel, a cryptographer at Trust Machines, who sadly is not here. It's a variation of Frost signatures from Chelsea Comlow and others from 2020. The key idea is that instead of everyone having to have their own public-private key pairs, there's a single aggregate public key that's represented as a sum of polynomials whose coefficients are curve points. There is a corresponding private polynomial for each signer, whose coefficients are scalars. Every signer has their own polynomial set. If you add all of them up and evaluate it at the point 0, you get the private key. But no one does that. No one has the private key. Instead, each signer produces a share of a signature, which, when summed, is a single Schnorr signature and can be authenticated with the aggregate public key, which in turn is derived from the public polynomials from each of the signers. Now, the key innovation of WSTS over Frost is that it has a notion of weighting each signature share. That's great because instead of there needing to be 4,000 such polynomials, so number of reward slots, which a system like Frost would require, we can instead reduce the complexity to the number of stackers, so number of distinct signing parties, which is about 10x smaller. That means that distributed key generation and signing rounds can happen very quickly, like on the order of seconds, which is necessary to meet our target block times. Now, this is all facilitated with a separate program called a signing daemon, which runs alongside the Stacks node to carry out this state machine for affecting group signatures like this. That is facilitated through the StackerDB system. So I mentioned earlier, the StackerDB system is an overlay on top of the peer network. So the way it works is some Stacks nodes can subscribe to, in this case, the POX4 StackerDB replica. Every stacker subscribes to it. When they run their signer, the signer stores DKG and signing state into the replica, and the replica, their local replica, talks to other Stacks nodes that know about this StackerDB instance and forwards those chunks along. So every node that subscribes maintains a full copy of that StackerDB. That's really important because it means that your signer daemon can be behind a firewall. It doesn't have to be a public node. In fact, it shouldn't be. It contains private keys. You don't want it to be public at all. I should point out, though, that signing key is not the stacking key. So your stacks are safe. That can be in cold storage. This is just for signing blocks. But people who are paranoid, like myself, could run the signer on their home networks. And as long as there are some public nodes that are replicating the state for the StackerDB, then my signer can talk to other people's signers, even if they're behind NATs. The final piece of enabling technology here is Clarity WASM. So as I said earlier, it's still WYSIWYG. You're still going to see your contracts in the Explorer. We're just changing the intermediate representation to be WASM and executable in WASM with a WASM interpreter. So, and compatibility is guaranteed here. The new Clarity contracts can still call into the old ones. When the system launches, we intend to keep the old intermediate representation around just because we want to make sure that everything is all compatible up until the beginning of the Nakamoto system. But after that, we can go retrofit it with the WASM interpreter and drop the old intermediate representation entirely. That would mean that boot up would go a lot faster. You wouldn't be using the old system to process the transactions during the epochs leading up to the Nakamoto epoch. Now here's the fourth big thing we're doing. We're addressing the Bitcoin MEV problem. So right now we've got a bit of a problem. F2 pool likes to censor block commit operations. And the reason they like to do this is because it makes them lots of money. It makes them lots of money because the current sortition algorithm, while it deprioritizes the likelihood of them winning, they're astronomically unlikely to win if they're just competing with the payouts they're currently doing and the behavior they're currently exhibiting. The current sortition system is such that if you are the only miner in that Bitcoin block, it doesn't matter how little POX payout you make or whether or not you mined at all previously, you're guaranteed to win. So what they've been doing is whenever they win a Bitcoin block, they block everyone else's block commits, they put in a very tiny block commit of their own, and they win the Stacks Coinbase. And they pay almost nothing for it. That's not cool. And moreover, that hurts Nakamoto because Nakamoto incentivizes stackers through POX payouts, and also it incentivizes SBTC through POX payouts. So we've got to stop this. So the way in which we stop this is we use a new type of weight function for the sortition algorithm called assumed total commit with carryover, or ATC-C. The key ideas are that even if you win sortition, even if you're the only miner, sortition might not even happen anyway if the total commits in that block are quote-unquote too low. The goal we're going for here is you have to mine at least 50% of the time at 50% of the total mining power if you want to have your guaranteed MEV behavior, which really forces the likes of F2 pool to behave much more like an honest miner. So instead of there being one throw of the dice to pick who the next winner is going to be, there'll be two throws. The first is to choose the winning miner. And the second is, if the commit value of that block is too low, we throw another roll of the dice to see whether or not a sortition even happens. And that's a function of how much you paid versus how much the past 10 blocks have paid in the median. So the first probability is just as what it is today. The probability that you as the miner win is equal to the minimum of your block commit, and the median of all of your commits. Today is the last 6 blocks, and Nakamoto will be the last 10 blocks, divided by the total commits in that block. A new thing here is that if your median value is 0, then the probability of you winning is 0. Right now, it's not 0. Right now, it's 1 in 2 to the 256th power minus 1. So it's basically 0. But if you're the only miner who shows up, you're guaranteed to win. So that's changing. You have to mine if you want to have a chance of winning at all. The second throw of the dice is the probability that a sortition happens. If the total commits in this block is less than the median of the past 10 blocks, then the probability that a sortition happens at all is the minimum of your winning commit and the median of your last 10 commits divided by the median of your last 10 commits. By I mean your last 10 commits, I mean the winning miner's last 10 commits. So what that means is if F2 pool has this really tiny POX payout, that's going to be a lot smaller than the median of the last 10 winning payouts. And so they're going to have a very small chance of winning sortition, even if they're the only miner who shows up. Like there might be like, 1 in 100 chance. If the total commits in the block, however, are still higher than the median of the past total commits, so that's indicating that this isn't an MEV miner block or the MEV miner is paying high enough, then sortition is guaranteed to happen. We're raising the floor of what's acceptable for sortition to happen here. So now the probability that your tenure happens is the product of these two probabilities. Probability of winning times probability of a sortition happening. So what that means for F2 pool is they better up their game. They have to start paying Bitcoin out at a rate equivalent to a 25% stacks miner. That means they have to be online at least half the time. That guarantees that the median of their commits is greater than 0, and the probability of winning is not going to be 0. And they have to, when they do mine, they have to pay half of the Bitcoin, that, i.e. the sum of all the other miners' Bitcoin, if they want to have a guaranteed sortition win. Otherwise, there's a chance they don't win, and that cuts into their profits. Now, this right here is probably the weakest part of the Nakamoto system design right now. This is discussed in the SIP publicly. If you have a math background, I'd love to talk to you. Perhaps we can find something better. This is what we got right now, and if left unchallenged, it's what we'll be proposing in the final SIP towards the end of the year. So in summary, we got our fast blocks. There's many stacks blocks per Bitcoin block. Signers are in the loop for producing those fast blocks in order to ensure that those blocks are widely replicated. That gives us no forks, because now stackers can compel miners to build atop the latest stacks block ever seen. When miners mine, instead of announcing their block on the Bitcoin chain, they announce a previous 10 years tip on the Bitcoin chain, thereby anchoring the stack's history to the Bitcoin chain in a way that makes changing that history later on as difficult as attacking Bitcoin. And we reduce Bitcoin MEV through this new weighting function, ATC-C, which raises the cost for an MEV miner in order to participate profitably. They can still make some money, they just have to behave more like a normal miner to do so, thereby ensuring stackers continue to receive a stream of POX payouts, thereby ensuring they will show up to sign blocks and they will show up to sign SBTC operations. So 2 things I'll leave you with here. 2 links. The source code to the Stacks blockchain where this is all being developed is here. It's github.com, Stacks Network, Stacks Blockchain. And the SIP, the Stacks Improvement Proposal that describes this system, is pull request number 155 on the stacks.gov/SIPs repository. And with that, I think we have a couple minutes for questions.
How do you plan to ensure blocks will happen in 5 seconds across the entire network?
So they can happen a lot. They can potentially happen faster. Stackers will just knack them to ensure that you hit a 5-second block time. When miners are mining, they're going through the mempool, they're picking up transactions. That miner thread has a deadline. So if they see that, it's been 3 seconds or 4 seconds, we better stop now and send this block out for the stackers for a collective signature.
Can you go into a little bit more detail on for the Clarity WASM part, the intermediate AST you were talking about, and how that's different from like a compiled language like Solidity?
Yeah, sure. So the key difference between this slide here, right? Okay, so the key difference between something like EVM and Solidity and with Clarity is that the compiler here is part of the consensus core. That's important because we don't have a problem that Ethereum does have. In Ethereum, you see the compiled smart contract on the Ethereum chain. Now, suppose there's a bug in the compiler. So I can show you the source code to my smart contract in Solidity, and I can show you the bytecode, but it's ambiguous as to whether or not, if there's any sort of, if the bytecode behaves differently than the source code, it's ambiguous as to how or why that happened. Is it a bug in the Solidity compiler? Am I being a nefarious actor by changing the bytecode before I deploy it? You can't tell. That's actually led to problems in Ethereum smart contracts because bugs in the Solidity compiler have led to smart contracts being published that don't behave the way the source code says they should behave. By requiring the compiler to be built into the blockchain this way, so thereby ensuring the intermediate representation is generated by the consensus code, we remove that ambiguity. If your contract behaves in a manner that is different than the source code specifies, it's a bug in the blockchain, and the correct remediation there is to do a soft fork or a hard fork to fix it. Whereas that's not true in the Solidity case.
I remember you saying that there's, for the Frost algorithm, there's 4,000 roughly like weighted things.
Yes.
So you said there could be about 400 stackers. Isn't that number of stackers or signers? Isn't that number of stackers like subject to change? And if it became more than 4,000, would that screw with the weighting or just scales appropriately?
Sure, so there's at most 4,000 reward slots active at any given time. That's just the way that POX works. There could be as many as 4,000 stackers, but in practice there's closer to 150 stackers at any given point in time. So while the system could work at 4,000 stackers, it just go a little bit slower. The WSTS innovation is that in the happy path, we only have to get signatures from 100 or 200 people. And I just want to point out, that's considerably higher than the state of the art now. Like something like Liquid, for example, I think has only 15 signers. All right. I see we're out of time here, so. All right, thanks everyone.